We're going to begin lesson 2.6. Today, what we're going to do is we're going to be comparing linear, quadratic, and exponential models based off a data set. A lot of this I actually did lesson, I can't remember now off the top of my head. It was in unit 1 where we compared linear to quadratic to cubic. Today, we're going to do linear, quadratic, and exponential models. All right, so this is just kind of walking you through what I was telling you a second ago, that we're going to go through linear, quadratic, and exponential. They're going to be the most used models that we'll have in AP Pre-Calc, at least by assumption from looking at what documents the AP curriculum has released. This is my first year. This is everyone in the nation's first year to have AP Pre-Calc. It's not just Skyline. It's the whole nation. This is the first year College Board is doing it. And based off what we can tell, it looks like linear, quadratic, and exponential are going to be tested the most. But you're going to have other models as well as we go. But that's all this is walking you through. Students will be expected. Do I know for a fact? When I say expected, do I know for a fact? No. We're going to be expected to determine which model is the best, and we're going to assume that it's going to be linear, quadratic, or exponential. Might not necessarily be, but that's the assumption for most of the time. Yeah. All right, so let's talk about the differences in these between as we get going. A linear model typically has a constant level of increase. Now, if you check this, if it's a model, is this data going to be exact when you look at this scatter plot? No, so this won't be an exact, but they should be somewhat similar, or somewhat, you could average them out and they would be very similar to one another. For example, what's the gaining? And you can write this in your notes here as we go. How much does it increase going from 1 to 2.6? It's increasing by 1.6. Now, remember, if you're doing AROC, it's actually change of y's divided by change of x. How much did the x change? 2. Now, that would matter because that would find your slope. On linear, the average rate of change literally is the slope. And my stuff just went out on me. Let's try it, see if it comes back. Okay, I'm going to write that in. On a linear model, the AROC, the average rate of change, literally is the slope. And so here, you can check these as we go down. This time, how much does it increase by? 2.4. Now, what's my change in x's? 2. Okay, and what about from here to here? Okay, so you can see right here, it's not going to be a perfect model because these aren't changing by the same. How much is this changing by? 2.3. As you can see, these aren't the same, but they all are somewhat similar, that when you reduce, I'm getting 0.8 here. Here I'm getting 1.2. Here I'm getting 0.7. And finally, 1 point would be, whoops, not 0, sorry, 1.15. Okay, we can tell what's the slope approximately looking like it might be. 1. Slope's going to be around 1. Anyways, when you're looking at this data, you can tell that this is linear as it goes across. So when it seems like it's a relatively, that's the key word, relatively constant rate of change, approximately 1, it's very similar to 1, you know it's linear. Okay, so hopefully that's just kind of a review. Quadratic is going to be different. If you remember, what happens with quadratic is you would get to not just the AROC. For the sake of time, I'm not going to fill this out. But not only will we need to do an AROC column, if it's going to be quadratic, what other column will we need to add?
The change in AROC.
The change in AROC. And that's where you would get a constant level, a constant value would be the change in AROC. Okay, so just remember that that's what you would be doing if we were looking at quadratic models. I'm not going to fill that in because it's a lot of extra time that we don't need, that I don't want to focus on today. But that's where you would get constant terms would be on this column. This would be relatively constant. I'm going to say that here, relatively constant. If you want to fill that in your own, that would be a helpful exercise. But the change in AROC would be relatively constant. This would not be. Now, because it has concavity, this would be always increasing or always decreasing if it were a perfect model. But finally, exponential. What it says, the output values are roughly proportional. So what's different is you're not subtracting like we were on quadratic. and linear. You wouldn't be just taking the second and subtracting the first. What you'd be doing now is dividing. And the change of x would tell you what root to take. So on this one, we're going to write this in just so you have it. Define your ratio, and I'm going to put an R there. Define your ratio. What you do is you would take the change of x, actually rather than writing it, let me just put it up here. How much are my x's changing by? 2. So it'd be a square root of 1 divided by 0.5. That's how you would find your R. I'm sorry, let me write it one more time, make it a little bit clearer for your notes. So if you made a column and you want to find your R or your base, I'll do a B for base this time. You take a square root of 1 divided by 0.5. That's how you find that one. Or this value here. Again, how much is my x changing by? 2. Let me change colors so you don't blend in what's what. This would be the square root of 1.9 divided by 1. Or here, let me skip on down. If you wanted this to change here, it's still a square root of 8.8 divided by 4.2. That's how you would find your B. Now, I don't have room for this one. I can pull it out this way, and it would. Now I do have room. 4.2 divided by 1.9. These should be relatively equal if you type those in. Now that's what it means by proportional. It means you have a relatively common base. So these would be relatively equal to one another. That column right there would be relatively similar. Relatively proportional is the word I use, so I'm going to use the same word. Relatively proportional. I'm trying to slide this down so you can see a little bit more. Relatively proportional. There you go. One more time. For exponential, what would this value be right there? That's the initial value. How do we know that's the initial value? That's your initial value A because it comes with an x value of 0. There you go. All right. With that, we're going to get started looking at models. So if you remember from earlier this year, when we looked at models, we can, let me do the scatter plot first, and then we'll kind of go from there. And I'll get to where I was about to answer. All right, let's go with 0, 11. Go ahead and let's plot that. 0, 11. So 0, 11, plot that point. 2, 8.2. 2, 8.2. And we're going to make some guesses as we go. I'm going to say that's about 8.2 approximately. 4, 5, or 5. 6 and 2.3. 6, 2.3. 8, -1. As you look at this model, what type of model would you assume this to be? Linear. Okay, and so what we would do is if we graph this in the calculator, we could get an exact, I say exact, it's probably not going to be exact. Will this be exact? No. But the calculator would give us the best type equation that goes through as close to all the points as possible. So I think it might be somewhat similar to that right there. That looks pretty decent right there. That might be the regression. What type of regression is this?
Linear.
All right, this is a linear function. Linear function. Now, for right now, we're not going to actually find the linear function. We're just going to assume the equation would be something like that. We're not going to find the model. Excuse me, the model. All right, what about part B here? Let's plot these and see what you get. Try to plot your own without looking at mine. So I'm working silent. All right, as I'm winding down, what kind of model are you thinking this might be? Yeah, it's looking quadratic to me. Let's see. I know this has a tool. I'm not sure how well it's going to work. So we'll try this out and see if it looks good at all. That model's not looking very good, but I don't know if it'll let me mess around much with it. Nah, I can't do much with that. Anyways, this would be a quadratic model. If we were going to try to do it myself, it looks like the center might be somewhere over here. I don't even know if that's actually, what would you call that point right there if it was the top? What's the actual name for that mathematically? You could call it the vertex. What's the other word we've used? A maximum. Yeah, this might go something like this. I have no clue, honestly, if we graphed it, how accurate this would be. So it might be something like this. I don't know if this would be going in between. I really, we'd have to graph it and look. But we're gonna have some type like this. This would be a quadratic model. Oops, quadratic function. There you go. It's quadratic function. Okay, what about part C? Again, same thing. Go ahead and graph it, see what you're coming up with. All right, what are you thinking this time? This might be exponential. It's very good. Ah, good, even better vocabulary. What did decay mean again? It's always decreasing. Decay means it's always decreasing. So with exponentials, they're always either doing one or the other. They're either increasing or they are decreasing. They are never constant or changing directions. So this would be exponential decay. Very good. I'm going to throw that in there. Exponential decay function. And I believe I have one more. Let's take a look at one more and see what we got here. Negative 2, 2. 3. Come on. Yeah. Yeah. All right, what about this one? This also is looking exponential to me. Now, if we had more data, we might be able to say, it's actually quadratic, but since we don't have more data as it goes to the left, the best we can assume that this is exponential. If you had more data, there is a potential that this could become a problem, but you'd have to have more data to really think that. What type of exponential function is this? Growth or decay? Growth. The reason it's growth is because it's always increasing. Very good. It's always increasing. Okay, so now to pick up what I was starting to say right before I looked at equation 1, if you remember when we did this in the past, we didn't just graph scatter plots and look at them. We use what's called a residual. So when we create a model, we can use our model to predict the values for the output given the input. Now the residual is not always accurate, so I'm going to skip down. You can read this on your own. That's why I wrote it in, so you could read this on your own. But the way you find your residual is you can take an actual output value and subtract it by what was predicted by your function. So the difference between the actual minus the predicted is what we call the residual. Now, I'm going to throw in something new today that I did not give you in the past, and that is the error. The error is equal to the absolute value of this difference, meaning a residual could be a positive number or a negative. But if I ask you what's the error, you only give me the positive version of that number. Does that make sense? So if the residual is 0.7, what's that mean the error is? 0.7. If the residual is negative 0.7, what's the error? 0.7. Yeah. So the residual can be positive or negative, and it indicates to you whether the actual was high, if the predicted was above or below the actual value. So if it's a positive residual, that means the actual was above the predicted. If it's a negative residual, that means the actual is less than the predicted value. But as far as error goes, you just list what the positive value of that is. Okay, so I'm going to add that in today now. So here we go. The weight of newborn babies can be modeled by a what type of function? Linear. So that's telling us right now what model we're going to use. For the first 4 months after birth, selected values for the weight in kilograms of a particular newborn baby are given on the table to the right, where T represent the number of months. So this is in months. Use the regression capabilities on your calculator to find a linear model. So we're finding what type of model? Linear. And they want it in the form y equals a plus bx. So not mx plus b, we're going to use a plus bx, which calculator has that. Okay, so let's go find our model here. I get my calculator. And on this one, I need to scoot it over this way so I can see my table. Where do I go to? Listen spreadsheets. So we're going to go listen spreadsheets. And they title it T and W. So I'll title mine the same, T and W. 0, 1, 2, 3, 4. 3.2, 4.2, 5.1, 5.8, and 6.4. After you type those in, what was next? Menu, statistics, stat calculations. Okay, what type of model were we looking for? Linear. And I'm going to choose the one that says a plus bx. That's what it asks us to find. Okay, so choose that. It wants to know the x list. What variable do we title our x's? T. So I'll put a T there. And what did I title my y's? W. W goes there. Now, pay attention where it's going to save the equation in case we need that later. Mine's going to save as F1. Check what your calculator says in case you didn't clear yours. I'll choose OK. And here's my equation. Did y'all get the same values as me? Make sure I didn't make a typo. Are you getting 3.34 for your A and 0.8 for your B? All right. How accurate is this? If it says 0.9887, is that accurate? Not very accurate. It's a good model. It's a good model. Okay. So y'all should have your values here. So my equation would be y equals, what do we get for A? Plus, what was the B? 0.8 x. That was our model in this equation. And it says use the model found in part A to predict the weight of this baby 2.5 months after birth. Okay, what is 2.5? The x or the y? The independent or the dependent? The x. So using this model, we would say that the y value at 2.5, so I'll do like y 2.5 here. The y at 2.5 will be 3.34 plus 0.8 times 2.5. You don't have to put that y with a sub 2.25, 2.5, but I'm doing that just to indicate what we're finding. Right. Now, one other thing you could do if you don't want to type it in like this and risk a calculation error on the calculator, remember you can press Control Dock to get a new page, and you could just go to calculator. Where do we save that equation is? What was it? It was F1. You can type in F1 of 2.5, and this would also give you the answer there, 5.34. Is that what you got when you typed it in the calculator? 5.34. 5.34, and that would be in kilograms. Now that's the predicted value. I'm going to write that here because we're going to need that for the next part. So this is the predicted value. All right, finally, part C says, let me go this down a little bit. It says the actual weight of the baby 2.5 months after birth was 5.5 kilograms. So what did they just give us right here? This is the actual. What is the residual for this weight? Now, what's the formula to find the residual? The residual is equal to the actual minus the predicted. So let's substitute. What was the actual? And the predicted? And what do we get? 0.16. All right. So this is the residual for the weight. And if that's the residual, what is the error? It's always just the absolute value of the residual. So I could have done it that way. I could have said it's the absolute value of the residual, which means it's the absolute value of 0.16, which happens to be 0.16. Okay, so that's our error. That's our residual. Did our model underestimate or overestimate? Okay, so here's the question. If the actual was bigger than the predicted, did we underestimate or overestimate? Underestimate. We underestimated. Underestimated the weight since the actual was greater than the predicted. Wait. Questions on that? Like that so you can see more of it. Okay. At this stage, I give you your first DOL. I'm going to let you pause and solve this one. This is data I pulled just a few days ago. So this is actual prices. When you look at this, this is not made up. This is actual data. I pulled this one off. I should have put the source on here, but this is the average price in gallons. Price of a gallon of gas for the selected years from 2000. Oh, that's where you can tell it's me that did it. Is this from 2002 to 2014? No. What I need to change that? Change it on yours. 2022. Okay, there's your DOL. I want you to solve that one based off the information given. All right, moving on. So using a residual plot. Now we did this before. That's why I say review here. A residual plot, it shows you the residual set for the data and how we know it's appropriate. This is key. It's in bold right here. How you know if it's appropriate is the plot should appear without a pattern. If when your residuals are in a pattern of how they are wrong, that's because you selected the wrong model. If it's in a pattern of how it's always wrong, that means you can predict how often it's wrong. That's because you used the wrong. The reason it's so predictable is because you used the wrong model. So residual, you want the residual plot the residual plot to be without pattern, okay? So here, when you look at this one, does this appear to have a pattern?
No.
It's pretty scattered all around. Now, it doesn't have to be like a line to be a pattern, but that's pretty much, it's kind of bouncing back and forth. This would be a good model. Let's see, what does the question actually say? An exponential regression was used to model a data set. The residual plot for the exponential regression model is shown above. What can be concluded about the appropriateness? So we're concluding about the appropriateness. That's what we're trying to do here. Of the model based on the corresponding residual plot. You could say the exponential model is appropriate. The exponential model is appropriate. Whoops, is appropriate. I'm going to write this word appropriate. Here comes some spelling. Appropriate since why? Why is it appropriate? Since there is not a pattern. Since there is no distinct pattern. Now you could say, well, I can predict that it's going to bounce back and forth. Well, that's just showing you that the model is really close. That the model is always within, it looks like it's within, what's the error? What's the greatest error on this positive end of the residuals?
2.
Almost 2. What's the greatest error on the negative end? Negative 1.5. So the error is within 2 units. The error is always within 2 units. And it's, you might be a little above, might be a little bit below, but basically you always are going to be within 2. That's a pretty good model. All right, so now let's go to the next one. I want to give you an opportunity to distinguish between, here, you can read the problem, but I'm going to give you 3 different models. And what I want you to do, let's see if I can get where you can see every model. A group of AP pre-calculus students used a set of data to create linear, quadratic, and exponential. After creating the models, the residuals are shown here. What I want you to do is decide which model would be best for the students to choose for the data and give a reason why you chose that model. All right, DOL number 2. All right, so picking back up. Example 4. Mr. Passwater hopes to make it to the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted in a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius r in feet. Should Mr. Passwater use linear, quadratic, or exponential model for this situation? Explain your reasoning. Okay, so this is when we got to choose. So you're painting circles. So let's think about, how do you paint circles? Well, you'd have a circle, and then what do you do to that circle?
You draw it. Color.
You fill it in with some paint, and then you would do another one. And you're going to try to come up with a model to predict how much paint you need. So you're hitting, oops, and then you go to fill this in. What kind of model could we be using here, given the variables they see? So what am I painting? Am I painting the circumference, the area? What am I doing? When you paint, are you painting circumference, area? What are you painting? Area. What's the formula for area? For a circle. It's pi r squared. You take your pi, you multiply that times the radius squared. Okay, he wants the model to determine how much paint is needed in quarts for a circle of radius r. So basically he's telling you this. The model will look like this. Given any amount of radius, we're going to need a certain amount of paint, which I'm going to call A. What type of model would this be? Not exponential. Not linear. Why quadratic? I should say not. What's happening to our radius? So let's just say the number was 1. What's 1 squared? 1, and you multiply it times pi. I'm just going to say 1 pi. 1 pi. Okay, what if your radius was 2? 4 pi. What if your radius was 3? 9 pi. Okay, this data, is it growing exponentially? Is it growing? Well, let's do one more and then we'll determine. What if it was 4? Okay, check this out. If we found our A rock, if we check, let's see if this is linear. If we wanted to see if it was linear, you check your A rock. What's the change from 1 pi to 4 pi? 3 pi. What's the change from 4 pi to 9 pi? 9 pi to 16 pi. Okay, are those constant? No, but if I do one more, what would you call the next one? Whoops, that's not a very good change. Let's try that again. Change of A rock. If I did this column as well, what's the change between these two? 2 pi and change here? What can you tell me? This is a quadratic model. And the reason is because the variable in a circle, what's the thing that's actually changing? Is pi changing? What's changing? The radius. The radius is your variable. And since the radius is changing and the radius is squared, it'd be quadratic. It's a quadratic model. And that's why. The radius is being squared. So that radius is quadratic since the radius is squared. Since radius is squared when you find area. Okay, after creating his model, Mr. Passwater uses it to purchase different special paint colors to be used on his mural. In this situation, do you think it is more appropriate for the model to underestimate or overestimate the actual amount of paint needed? Would it be better to underestimate the amount of paint we need or overestimate? Why overestimate?
You might run out. And then
Overestimate so that we can complete the project, or he in this situation can complete the project, or maybe, or I want to say touch up. Y'all know what I mean when I say touch up?
Yeah, like little.
If needed, if necessary. So it's more important. What would happen if you underestimate? It'd be embarrassing. You ever seen someone start to graffiti up something and cops showed up and they had to run off and it looks unfinished? Some of y'all are like, no. Okay.
Or see like the rain coming in and it's starting to dry again.
Yeah, there you go. So that's the idea. You want to overestimate, you want to be able to complete the project. This was obviously done in a legal matter, but all right. So we're overestimating the detail here. All right. So I have a DOL for you. I'll let you think on this one. And I have this last review question for you. Finish this up. I want you to think on this here to describe the end behavior. What does the end behavior mean? The limits, the end behavior would talk about not where the graph is, it's telling you where the graph is going. I want you to think of, this is what you said. I want you to think about if you graph this, what the function would look like, and you're going to write two limits. You're going to write about as t would go to negative infinity, and what happens to the y values, the f of t values, as t approaches positive infinity. I want you to think through what would happen on this graph as t increases or decreases without bound. Let me change this to a t here. Y equals f of t. There you go. I want you to fill that in to complete this DOL.